And
Hi, Gaurav.
hi, Gaurav. We hope you are having a wonderful interview. Good luck to you. Let's jump on in. And what better way to have a collaboration Wednesday than to do separable differential equations? You've done them before, and this is so wonderful that today's lesson is going to be super short. You've got a first order, let's say dy dx is equal to a function of x and y. Let's just say that you only had a function of x. Multiply both sides by dx. You could integrate, as you can see here at the bottom of the screen. And taking an antiderivative of g of x, you get capital G of x. Look at that. What are we talking about? Well, let's do one in super detail. dy, you could envision, would look to be something like this. Let's multiply both sides by dx. This is a particular problem, and all of a sudden kids will say, well, hey, how about we integrate? You bet. What's the integral of dy? We just get y. What's the antiderivative of x squared? We get x cubed over 3. Ooh, reverse the chain rule. I hope you remember how to do that. E to the 3x over 3. What's the antiderivative of sine? Negative cosine. Don't forget the pesky little constant. Done. Wow. All right. Well, very often our separable differential equations will have a product of a function of x and a function of y. This is definitely not the proper math vocabulary to get stuff with y's and dy's together, but you get the idea. We're going to move every term with a y in it over with the dy, keep all the x's with the dx, and then we integrate and we do the problem much the same way we just did. For example, let's take a look at this problem right here. Dy dx equals y plus 1 all over x. Tell you what, I'm going to simultaneously divide both sides by y plus 1 and also multiply both sides by dx. And I hope very quickly we see this is what we have. Oh, this is a great problem, fantastic problem. Obviously, we're going to integrate, but do we need to remember a few things? What's the antiderivative of 1 over y plus 1? Do you guys remember that? Yeah, ln of absolute value of y plus 1. And how about the antiderivative of 1 over x? Natural log of the absolute value of x plus some constant. And my goodness, hello. Yeah, 1 second. There you go. Starting off with this, I think right now it's the absolute value that might get kids a little bit uncomfortable sometimes. And we do need to discuss that. Solving for y, though, what should we do to both sides, guys? How about we exponentiate? Right? We're going to raise the right side and the left side. E to that left side power, e to the right side. And real quickly, the left side, I hope kids are usually feeling pretty good about. That's y plus 1 in absolute value. And before we go much further on this right-hand side, let's also talk about the following. That if I gave you x to the a times x to the b, what was that back from basic algebra days? X to the a plus b. Did you know you could go backwards with that? This would become e to the natural log of the absolute value of x times e to the c. And what is e to the natural log of x? That would just be absolute value of x. E to the c is some other constant. How about I call it C2 or C sub whatever you like. And that's very helpful because e to that constant is just another constant itself. But now we're faced with this kind of other puzzling situation. Sometimes kids are like, wait a minute, how do I solve explicitly for y? wow. Well, let me ask you this. If two absolute values are equal, maybe a little bit of side work, guys. What if I gave you the absolute value of W was equal to the absolute value of U? Must it be true that W and U have to be exactly the same? Not necessarily. Certainly it could be. What else could happen? U could be the opposite of W or vice versa, right? So in other words, if we're thinking about this, we could very quickly say, now hold on a second, y plus 1 then should be plus or minus c sub 2 of x. That's what we're really getting at. Saying that the two absolute values are equal is allowing for their arguments to either be exactly the same or to be opposite. But now here comes another clever little trick. If I took plus or minus a constant, wouldn't I still have just a constant in the end? Think about that. C2 is just some number, right? And inherent with the phrase arbitrary constant, guys, is the implication that perhaps it's positive or negative, isn't it? So put a plus or minus in front of a constant, you really haven't amounted to saying very much at all. You're saying it's a constant. So we call it C sub 3. You know, who knows what it is? Somebody could say, but it could be positive or negative. So could C sub 3. Right? So what would we say here for a final answer? Well, we could say y would equal C sub 3x minus 1. Very often the author could even sneak in saying, look, it's some arbitrary number A. All right. Well, one more problem, and then we are through. Hooray, hooray. Look at this. dy dx is equal to the opposite of x all over y. Well, separate the variables. You know the College Board was just obsessed with that. We talked about that so much last year. Why don't we just do a little cross multiplying? Take a look at that. Integrate. And what do we get? What's the antiderivative of y dy? Y squared over 2. How about over here? Negative x squared all over 2 plus a constant. And sometimes kids look at that and they're like, wow, wait a minute. Yeah, tell you what, how about we bring over that x squared over 2? Now how about we multiply through by a 2, and I heard somebody say that over there. What kind of shape is that? It's a circle. Oh my goodness. Wow. And again, what you might see in the back is someone just writing an arbitrary constant C2 there. Because again, whether you're saying I'm doubling a constant, well, you double a constant, guys, you still have a constant. And it's very possible that they won't even leave the subscript. So, that's it. Tomorrow, even better news. Same stuff, but we're going to throw in an initial value. It'll be like, we've done that before. You bet. All right, let's get to work.